All right, dual enrollment stats class. We are finishing up chapter 10 today with this lesson. I don't imagine this is going to take the entire block to do. So once we finish, you should be able to attempt all of the chapter 10 questions. There may be a few exceptions of things that possibly these notes had missed. So if you run into anything, you're like, I don't think that we covered that, just feel free to ask your instructor, and I can make a follow-up video in the next couple of days to help explain all of that. But we got the 10.3 notes. It should be the last section in your little notes packet for chapter 10. This is the page that we're looking at. And so I don't really want to start with all of this information. There's a ton of rules here as far as taking tests for population mean. What we had learned on Tuesday, the 2nd of April, was proportions. We learned how to do a hypothesis test with proportions. We learned how to make the hypotheses, create the hypotheses. So we're going to practice that again today. But I want to come back and talk through all of this. And I want to jump straight to the example 1 down here so that we can talk through it. I think it's helpful to start with the example and go through the different properties, the different rules that are on the first 2 pages on here. But let's start with an example and see what it says and how we approach running a significance test of example 1. So you should have enough space to write underneath this, hopefully. If not, maybe you can just use this last page, the back page here, just draw a line and you can write example 1 up here if there's just not enough space, because we will be putting a lot of little notes and stuff. I don't know if this is enough space to talk through all of them. And I, as a matter of fact, have moved this over to a Word doc so that I have plenty of space to work. So let's look at this. So it says, assume the resting metabolic heart rate of healthy males in complete silence is 5,710. I don't really know what this unit of measurement is, but here we have something that's known to be true. So we're already sort of, like we talked about on the 2nd of April, the idea of what is known to be true, right? This is already forming up to be like a null hypothesis, okay? So researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean RMR to be 5708.07 with a standard deviation of 992.05. At the alpha 0.05 significance level, is there evidence to conclude that the RMR of males listening to calm classical music is different from the 5710? Okay, so as we begin this, and of course you're writing this on the in this part here, we're going to go ahead and put the null and alternate hypothesis in here. So I'm going to be drawing that. So let's start with our hypotheses, HO and HA. So we practiced doing this on Tuesday the 2nd. But today we know that we're interested in means. Okay, so if you want to underline that, we're given the standard deviation. I know we had worked on trying to figure out which one am I working with. Well, we see the word mean. We're pretty sure that we're dealing with means. So right now with our null hypothesis, we know that the mean is, and forgive my drawing. I'm using just the mouse and keyboard here. So I'll redraw that one more time just to make it look a little better. But the mean that they're saying, what's known to be true, is this 57. 10. That's what it's known to be. Okay. And what we're trying to show is that mean, we've already talked about, we know that these should always be the same here. But here, this connective, we just need to know what it is. And we'll notice that it says is different than the 5710 per day. So that just means it's not equal to. So we're just trying to show that it's not equal to that value. Okay. So what we're going to begin with, and what we're trying to do is we're trying to say, okay, we have our sample. They took a sample of 45. So N equals 45. That's a pretty large sample. I think we'd all agree that that's plenty of data. And they got a mean of of 5708.87. So that's X bar is what that is right here. This is X bar. So we'll write that out. 5708.07. And then we have our standard deviation of 992.05. That is just S. That's how we've seen that symbol in this class. So S. And we're going to write up that number, 992.05. Okay, so is this different enough? It seems to me like it's actually pretty close to, like if we look at these values here, like these seem pretty close, and the standard deviation's huge. So this seems pretty plausible, okay? This seems pretty plausible as far as a value to get. I don't think this is extreme enough to make it seem like anything has changed. But we're going to go through some properties to help us think through this. So we, back on the very front page, when we're testing hypotheses regarding the population mean, assuming the population standard deviation is unknown, which this is true right here. We don't know what it is. Standard deviation is unknown. We are going to use the t distribution. So we've been using, remember we did t intervals and things like that rather than the z distribution. And we replace sigma with s. So we've learned about this t distribution and the degrees of freedom. A lot of StatCrunch is going to do this for us. But we've seen how the t distribution works. It's centered at 0 and is symmetric about 0. And the area under the curve is 1. And because of the symmetry, the area under the curve to the right of 0 equals the area under the left. I'm going to go ahead and pull this up in StatCrunch. And if you want to have this open, go to calculator's t distribution. We've already seen this distribution, but that's what is going to be created. The sampling distribution of our statistic will take on these values. Okay. So these are just all the properties of the t distribution, and we've kind of already gone through how this operates. If I increase the degrees of freedom, that makes it wider, and as I increase this, it gets closer and closer to what would appear to be a normal curve. The lower it goes, it gets a little more narrow, and there's more area out in the tails. It actually has more area out there. But we're going to be using the t distribution because we don't know what the population standard deviation actually is. We have the sample standard deviation. Okay. So what we're going to build, let me go back to our original notes here. Testing hypothesis regarding a population mean. So to test hypothesis regarding the population mean, we use the following steps. The samples obtained using random sampling. And that appears to be true right here. Researchers measured, it doesn't say it's random here, but we'll assume that the researchers know what they're doing and they used a random sample of 45 individuals. Okay. The sample has no outliers, and the population from the sample is drawn as normally distributed or a large size. So this is true. We know that our sample is 45, so we're good. And the sample values are independent. We've already determined our null and alternate hypotheses, and we have these three ways. Ours is a two-tailed test, so we'll add that. This is two-tailed. So two-tailed. Okay. So we'd already worked through that a little bit on Tuesday. And then we select the level of significance alpha depending on the seriousness of making type 1 error. And we had talked about the types of errors, so that is should be fresh on your mind from Tuesday. And alpha is the probability of committing type 2 error. I think that was something that I did not write about. You may want to write that here. Alpha is the probability of committing error. Okay, so we can kind of just write that right there. We'll have Grammarly help me out. So we You can add that note just right here underneath step 2. So we have a classical approach, which is we compute the test statistic, and so we'll talk about what that actually means. Actually, strike that. We're not going to do this classical approach to this. So if you want, actually, you can cross through that. We're not going to be computing the test statistic. We're going to be using the technology to do this instead of this test statistic. I mean, we can still find the test statistic. We call it the critical value. It's basically a z-score, but we're going to have the computer calculate the p-value for us, because we know that we need that p-value. That's something that we had learned, is that we need a p-value to be able to do this. So we have all of our statistics, so we want the p-value. So that's going to be the next thing that we write down. So p-value. And you might want to write down these steps. We're going to show how to do this in StatCrunch. I'm going to split my screen up here. We'll go to StatCrunch. We won't be using this T calculator specifically, but in order to get our answer for this question on our notes page, we're going to go to Stat, T-stats, one sample, and we have the summary. Okay, the next example we're going to do will be with data, because you can see it's listed the data, but right now we just have the summary. So we're going to go ahead and click that. Okay, and it's very straightforward what it asks us to do here. And let me got enough room over here. So look on the left side of the screen. We'll put in our sample mean. We know that they got 5708.07. The sample standard deviation is S, so that's 992.05. And then the sample size is 45. So we don't have to worry about degrees of freedom or anything like that. We do need to test this hypothesis. So we're going to type in our 5710. And we're just saying it's a not equal to. Okay. We don't really need to touch any of these other parts of this. We're just going to hit compute. Okay, and so this gives us a p-value of 0.9869, so 0.9896. I think I said that backwards, but right here, this t-stat, by the way, that is the z-score. If this were to show up, if I go to my t calculator, basically the degrees of freedom for this is n-1, so this is 44. And if I put in where this lands, so we'll do, it's just barely below the mean. That's really what this is saying, is it's just barely. So we notice that our sample here, this is just below the hypothesized mean. Okay, and so that's why this like sort of z-score, they call it the t-stat here, this is the critical value, which is a z-score, is just barely to the left of the mean overall. Okay, sure I can show all this, covering it up. So this is like me putting that t statistic in there, which is this negative negative 0.01305. And you can see, so this is the probability that it would be less than, and what the calculator is doing, since this is two-tailed, is it's taking that value 0.4948 and it's just doubling it. And that's how they got the 9896 there. But you don't really have to worry about any of this. This is like, as usual, I say I do the theory. This just gives you the p-value. And now we know that we can create our conclusion. Okay, so that's what we're going to do next on here. It's down. So let's form our conclusion for this problem. I think maybe you have run out of space by now, maybe not, but let's write our conclusion. And so the conclusion is, since the p-value of 0.9896 is greater than alpha equal to 0.05, So since that's so high, it's greater than our significance level here, we fail to reject. I'm going to actually underline that. Fail to reject. And then we will put H0. Okay, the null hypothesis. And basically what that means is there is not convincing evidence that, well, what were they trying to show? They're trying to show that the resting metabolic rate for males listening to calm classical music is different than what they'd said here. So that the mean RMR of males listening to calm classical music is different than the 5710 kj per day. So there is our conclusion, and that's what we would want to pick for those options within the MyMathLab. Okay. All right, so that is the first example there. So in hindsight, looking back at all of these notes here, we really aren't using a lot of these here. We're really just using the StatCrunch to do this. Just don't forget that for whenever it's means, we're doing stat, t-stats, and right now it's one sample. We just did one with data, but we're going to go ahead and do the next one. We're going to look at this one here. Okay, we're looking at quarters, the weight of quarters. So I'm going to go ahead and copy this into Word so that I can write on it. Okay, so hopefully you have enough room for this in your notes to fill this in. I think you should have room down below here. And then of course we'll talk about practical versus statistical versus practical significance a little bit. Let's go ahead and show how this would work. Obviously, if this were in StatCrunch, a lot of times it copies and pastes for you, but we are going to need to actually type this in ourselves. So over here, we're going to call this weights. That's going to be our variable here. But before we even type this in, let's go ahead and set up our hypotheses. Let's do that first. So it says, according to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. At the alpha 0.05 level of significance, is there evidence to conclude the quarters have a weight different than 5.67 grams. So we can see again that this is just asking for it to be different than that. Let's go ahead and set up our hypotheses. Okay, this is means. We see the word, let's see. It doesn't really say mean on here. We don't see the word mean. We don't even see the word standard deviation. But I'll go ahead and tell you, anytime you have data like this, okay, anytime you see data that's especially quantitative data, that's when it's means. Because with this data, we can calculate a mean and a standard deviation. So this will be mu, and it's known to be 5.67 grams is what we're working with, but we'll just leave it as 5.67. The alternate we'll put 5.67 again. We know that this one is different than, so again, this is two-tailed once again. And so now we're going to type this into StatCrunch over on the side. I'm going to go ahead and we can pause the video. I'm not going to sit here and just type all this in front of you, but you can pause the video and get that. Everybody can type that in on StatCrunch and then press play again once you're finished. Okay, so I've typed mine in. I moved them over just so you could see the data. So we typed all this data in, and now what we're going to do, when we do our t-stat t-stats here, one sample. We're using with the data now. We don't need the summary. We don't need the X bar or the standard deviation. I mean, we could find it and then type it in that way, but we have the data, so we're just going to use that. So we're going to click weights as our selected column here. It's the hypothesis test for means, and we're doing 5.67. And again, you'll notice it auto-fills down here, but yeah, it's a not equal to. And yeah, we're ready. We're going to hit compute. And we can see that this p-value is quite a bit different. Our average was 5.7, by the way. And this is our standard error right here. And so 5.7 is seeming to be far enough from this mean based on the sample size and everything that we end up with a p-value. So we'll write this down, p-value equal to 0.0136. Now, is that low enough? Well, compare that to the alpha level right here of 0.05. Yeah, I would say so. That's exactly what we found, is that there seems to be a statistical difference than with the state coins than just a typical quarter. All right. So let's write out that conclusion. I'm going to move this down. All right. So conclusion. Since p-value of 0.0136 is less than alpha equals 0.05, we reject the null hypothesis, reject HO. So we're saying that there's a difference. So that's the next sentence. There is convincing evidence that that the state quarters, we can really just retype what this last question has asked here. Okay, so I'm just pretty much copying that. Have a weight different than 5.67 grams. And that's it. That's how we do this. So we were able to answer both these questions, and really that's what you're going to be looking for to do on your MyOpenMath when you work through that. Okay, so we're going to talk about statistical versus practical significance. So the average age of a mother at the time of her first childbirth is 25.2. That was in 2003. So that's kind of our null hypothesis. We're going to go ahead and get StatCrunch going. We're just going to run this test. We're not going to write up a whole bunch with this. So in StatCrunch, for this problem, I guess I will write up the null and the alternate hypothesis. So the null is that the mean age is 25.2, and our alternate is that right here it says that it's increased. Okay, so here we're trying to show that it has gone up. So it has gotten greater than that value. And as you can see, 25.5 is greater than, but how is that far enough to really make a big difference? Like, will we even find practical significance within this? So we're going to do our t-stat, one sample, and we have the summary now. The sample mean we got was that 25.5, and they tell us the standard deviation is 4.8, so that goes here. The sample size they took a huge sample size, 1,200. Okay, 1,200. And they're trying to show that it's different from 25.2. Now we'll hit compute. Okay. And so, yes, they did, even though it wasn't that too far of a difference, we did get a p-value that's greater than. Now I want you to try this. Let's actually edit this. Imagine they got the same results with a sample of, let's just do 120 people, and then we hit compute. You'll notice that p-value goes way up. It is way larger than with the 1,200. Okay, and so that's what this last note is on the back here. It says large samples can lead to statistically significant results, while the differences between the statistic and the parameter is not enough to be considered practically significant. Like, these two numbers are pretty close still, but a lot of times this happens in stats where your sample, you take such a large sample. When a large sample is used in a hypothesis test, the results could be statistically significant, even though the difference between the sample and the sample statistic and the mean stated in the null hypothesis may have no practical significance. Okay, so while technically, I'll change this back to 1200. So while technically the p-value is on this one 0.0306, which is less than alpha. So we would reject and we'd say, okay, yeah, it's gone up. It doesn't seem like it's that much more significant. Okay, it's practically not that much more significant. So I want to talk about the assignments that are on MyMathLab. So I know that 10.1, you should be good. 10.2, you should be good. We did proportions just fine. This is what we learned today, was the 10.3, a one sample t-test. That's what we just learned. And you've seen how to do it with summary or data. And then 10.4 is just going to be a mixture of proportions and t-tests. So you have to read the scenario and decide which tests you need to use. I do want to look at a question on this, and this may pop up in 10.2 as well. But I do want to show you how a question like this would work. We talked a little bit about, we just briefly mentioned the idea of the t-stat right here. This t-stat is actually pretty important to use. So the t-stat is really what this is. So this is t sub 0 right here. That's what would go here. So if I'm working this question on, it's question number 1, and I imagine many of the other questions are going to have this process. I'm just going to work through this problem. If you want to work with me, you can. But here we know it's a t-distribution. Here's the hypotheses. They give them to us in the original question up here. So we have that. It tells us the sample size, and it gives us the mean and standard deviation, and it wants us to compute the test statistic. So to do that, we do t-stats, one sample, and we have summary. Gives us the mean, 57.2. The standard deviation is 14.6, and the sample size is 26. They told us the hypothesis. It's up here. So 60 is the value. We don't even know what the context is. So this is just us practicing using the tool, really. And it tells us that it's a left tail test, and that's all we need to do. We're going to hit compute, and right here it gives me the p-value, and this is something that I need right here. I need the test t-stat for this one. So this is going to be negative 0.97789. Round to 3 places though, so it's 978, and I hit check. We got that correct. Okay, if the researcher tests this hypothesis at the alpha 0.1 significance level, determine the critical values. It says, although technology or t-distribution table can be used to find this, in this problem, use the t-distribution table given. Interesting. Let me check real quick to see if the technology does this for us just fine. So it looks like the technology is not going to work. In here, we have a critical value. And as the problem said, technically, the technology is like correct. This is more accurate technically, but it does say to use the table. So let's talk about how to use this, because it looks like you're going to have to use it. So this critical value is basically saying if I get a value that's more extreme than this one here, then I'm going to reject the null. Okay, that's what a critical value is. So if this had been more extreme than this value, then we would have rejected the null hypothesis. Okay, the p-value represents that as well. Like the p-value is the probability that I would get this right here, this value, which creates the z-score right there. Okay, but this is not extreme enough. Remember how we said usually anything more than 2 deviations is extreme? Well, since our alpha level's 0.1, which by the way, if we look at our table on here, all of these up here are the alpha levels. So like this is our alpha. Alpha is 0.1 as the problem declared. Okay. And so that's our alpha level. And what we do is we scroll down and we look for the degrees of freedom. Well, what is our degrees of freedom? It actually tells us right here, 25, because our sample was a sample of 26 as stated in our problem. So the degrees of freedom is n minus 1, but you can always just find it here. So in this column here of 10.1, I go down to 25 and I see 1.316. Second. So yeah, I typed that in, -1. I did the negative though because it's to the left. We have this negative value. It's to the left. You'll notice that table is the table's all positive values. It is important that if you're doing a negative, like if it's a left tail, you change these to negatives. So all of these, by the way, are just z-scores. Okay, all of these are just z-scores, but we had to pick the correct direction on those. Okay. And then you draw the t-distribution. So those notes actually were kind of important, but we know that this is a left tail, so that's how you want to be thinking about this. We're looking for the diagram that is to the left, so this would be the best one to pick because it's to the left. Okay, and that's the best way to remember how to answer like these little graphs like this. This would be two-tailed over here. This is left-tailed and this is right-tailed. And that's all based on the symbol in the null hypothesis and the alternate hypothesis. So will we reject the null hypothesis? Well, we should not, because the p-value is not low enough. Also, this t-stat is not further than this. So no, the test statistic does not fall in the critical region. Okay. So that would be the best because it doesn't fall in this blue region. This is not further than this. We are not going to reject. Okay. So it looks like I'm going to look through some of the remainder of these to see if there's anything that stands out. I'm really glad we did that question. Yeah, it looks like the rest of these should be pretty good. So that's going to conclude this chapter 10 set of notes. So you guys can now start working and making sure you have the chapter 10 My Math Labs worked on and completed today and tomorrow. And then we'll start chapter 11 next week and get through that. Okay.